Hi, in this video, let's discuss a few of the limit laws. As you know, the concept of limits forms the foundation of calculus. We have discussed the concept of the limit in an intuitive way, avoiding all the formal definitions. Now today, let's try and see what kind of algebra applies to these limits. So here's my first example. Suppose f of x equals 1. So you're familiar with that function. Its graph is a horizontal line. We would like to ask ourselves, what is the limit of this function as x approaches a? A could be any point on the number line. As you can see right away that the limit is in fact 1. There is not much to discuss. This same fact, we can also write it in this manner, limit, and here we just put in whatever formula we have for f of x. In this case 1, it's a constant function. So I can put limit of 1 as x approaches a. What is that? It's in fact 1. So this 1 doesn't have any x's in it, it's a constant function. And so keep this in mind along with this picture. Now we can generalize this discussion to this observation. Limit of c, where c is any constant number, as x approaches a. What is that? That's simply c. c is a number, it doesn't have any x's in it, and so the limit of c as x approaches a, we conclude, is in fact c. And this simple example should convince you of why this is so. If we had approached the concept of limits with a rigorous definition of limits, we would be proving this. But right now we are taking an intuitive and informal approach. So this little example should convince you that this is true. So similarly, there are a few other facts about limits that I would like to go over with, and then finally summarize our discussion with limit laws. So let's look at the next example now. Here I have f of x is the function x squared, g of x is the function x cubed. Let's look at limit of f of x as x approaches 2. So 2 is a point on the x-axis. And as you know, we can rewrite this in this form. Limit of x squared as x approaches 2, because f of x is in fact x squared. You've seen this notation before. Now convince yourself that this limit is exactly 4. You can either construct a table of values, as we've done in another video, or you can sketch the graph of f of x equals x squared. But you convince yourself that this limit is in fact 4. Same thing for limit of g of x as x approaches 2. We can also write it this way and convince yourself that this limit is exactly equal to 8. Now let's look at the following. Let's say we create a new function whose name is f plus g. The usual way, which is f plus g, if it's a function, that means it takes an input x. And now what output do we assign to this input? Well, since f and g are functions, this is how in fact the usual way we define f plus g. F plus g of x is in fact f of x plus g of x. I'm sure you have seen this way of creating new functions. Now f of x plus g of x is simply x squared plus x cubed. So f plus g of x is x squared plus x cubed. Now say we are interested in finding this limit of f of x plus g of x, or this, it's the same thing as x approaches 2. f of x plus g of x is in fact x squared plus x cubed. So let's write it this way. We would like to compute this limit. So once again, convince yourself that this limit is exactly 12. You can either construct a table of values for x squared plus x cubed. So the first column would be values of x that are very close to 2. And the second column, you would calculate x squared plus x cubed for that corresponding values that's very close to 2. It's easy to convince yourself that 12 is the limit. Or you could sketch the graph of x squared plus x cubed and you would get the answer of 12. You might be thinking, but I really thought it would be 4 plus 8. I've already calculated limit of x squared as x approaches 2, limit of x cubed as x approaches 2. You might have that intuition, and you're correct. In fact, the limit that's calculated only by looking at x squared plus x cubed either the graph of it or the table, and carrying it out intuitively and getting 12, that 12, you're correct in observing, isn't that exactly same as 4 plus 8? So if you thought it that way, that means you already have an intuition for a certain limit law. Your intuition is telling you how to do the algebra with limits. And now let me show you all of the limit laws, which should feel pretty natural to you, the algebra that goes with the limit laws. So let's take a look at them. So here are the limit laws. Suppose limit of f of x as x approaches a is a finite real number L, and limit of g of x as x approaches a is another number that we call m, and assume that the number c is a constant, where if you see c down here. And here's the first limit law. Limit of a number c, a constant number c, as x approaches a is c. This is the example we discussed. So if you keep a picture in mind for this one, this limit law will seem like it's natural and it's believable. And here it says limit of the sum of two functions as x approaches a. If you have to find such a limit, it's all right to find individual limits. So limit of f of x, which we said is L, then find the limit of g of x as x approaches a, which is m, and then add those limits separately. This is same thing with plus replaced by a minus, so subtraction law for the limits. And here we have the product law for limits. If you have two functions and you're multiplying them together to create a new function, and you would like to find the limit of this new function as x approaches a, what this law is saying is it's okay to find the limit of this function and then find the limit of this function separately as x approaches a, and then multiply those two numbers together. And once again, we're keeping our discussion at an intuitive level, so no formal proofs. You can convince yourself of this by taking two functions, f of x, g of x, finding the limits separately, and then creating a product and finding the limit of the product as x approaches a, and see if this is true or not. So you're just informally convincing yourself, no formal proofs. And here number 5 is, you can think of it as a special case of 4. So if you ever find yourself in this situation, limit of a constant number times a function, and as x approaches a, see, it's almost like you can pull it out of the limit, and limit of f of x as x approaches a is L, and so that's how you get c times L. So again, only an informal way of explaining these, so you'll remember them. Finally, limit of the quotient of two functions. It is pretty much what you were probably guessing. Take the limit of the numerator, which is L. Take the limit of the denominator, which is m. It's L over m, except you want to be careful that you can only apply this as long as m is not equal to 0. Because as you know, division by 0 is undefined in math. So keep these limit laws in mind. They shouldn't be very hard. They feel very natural, that they feel as though this algebra is intuitive, and this is how limits should behave, and so on. So in the next video, I will show you an example where these are given, and then will use the limit laws to find limit of some of the new functions created from f of x and g of x. So that's one way you will use the limit laws. But the more important application of limit laws is on the topic of continuous functions. So many theorems about continuous functions use these limit laws. When we talk about continuous functions in another video, I will only keep our discussion at an intuitive level, and so we will not get into any formal proofs, but I will be mentioning the limit laws there. Thank you.